That's 90.
Yeah.
All righty. So let's go ahead and get started. First of all, I just want to make sure I didn't miss anybody for attendance. Is Diego here? Diego, last name is Curiel. And how about let's see, Sheldon? Oh, and then Emily. Emily here. The last name is Rosales. Okay, so let's see. We got 4, 8, 11, 16, 23, 27. So yeah, I can get 2 people to see. All right, so this is CPE233, computer design with assembly language programming. My name is Gary Perks. I go by Gary by my first name, line. I recognize a lot of you. Some of you were in my 133 class last fall. I think a few people might have been in my circuits class, maybe a couple of online people, I think. But I don't know all of you. Hopefully those that I don't know, I'll get to know your names quickly. Usually in a class like this, which is a studio type format, where you know, you have lecture and lab in the same on the same day. Usually I get to learn people's names pretty quickly. Okay. All right, so as you're probably aware, the prereq to this class is CPE133, the Intro to Digital Design class. And you know, sometimes you take a class and there's a prereq and you wonder why that class is appearing. Hello, are you going to go for him? But that's not the case with this class. You know, CPE133 is a real important prereq for this class. And you're going to see, I'm going to review a few things from CP133 in today's class. I'm not going to review the whole course. I'm just going to review what's particular to this class. Okay, and typically I'll do that at the beginning of a lecture. You know, whatever you need from CP133, you know, I'll go over. Now, there might be some times that I miss something that maybe I need to go over from 133, and you can tell me. Okay, but I have some planned topics from 133 that I, you know, think are important. Okay. Now let me tell you right off the bat. You know, I'm an honest person. I think people have had me in previous classes. They'll say, I think most people would say I'm an honest person, and I got to tell you, this class requires a lot of work. Okay, there is just no way around it. You know, you're going to be using Vivado, you know, Verilog or System Verilog, what you learned in 133, to build a microcomputer. So at each table, I put this diagram. So you're going to build this. Okay? You're going to build it piece by piece. So you're going to be using what you learned in 133 about modeling hardware, right, on the basis board using Verilog or System Verilog, depending on what instructor you had. By the way, I teach System Verilog. If you want to use Verilog, that's fine. I'm just not as familiar with Verilog as I am with System Verilog. If you know both, or I think if you ask people that know both, they would tell you that System Verilog is easy. Right? The System Verilog is like Verilog 2.0. It's an improvement over Verilog because there's not as many things you have to worry about. You know, like in Verilog, you get to worry about reg and wire. And System Verilog is just all logic. And then also there's something in Verilog where you only have an always block, where in System Verilog you have always FF and always tone. So, but that's okay. I will have an ISA for this section. Derek is going to be the ISA, and I think he knows Verilog pretty well. Okay, so the reason why this class requires a lot of work is you're going to be building this and then also learning how to program. Okay, learning assembly language. Okay, assembly language is a language that's closer to the hardware. It's closer to the zeros and ones, as opposed to high-level languages like Python or C or something like that, okay, which is like a tier above assembly language. Some people love assembly language. Some people hate it. You know, it's one of those love-hate type things. Very few in between are meant. Okay. So the reason I mention this up front, that this class is a lot of work, is you know, if you've got a busy schedule, like if you're already taking 20 units or whatever it is, or you're working a lot this quarter or whatever it may be, if you're not going to have the time for this class, I would strongly recommend that if at all possible, you delay it till you have more time. Because this class, I would say, is kind of like a class and a half, right? Because you've all taken a computer programming class, right? Usually computer programming classes, unless you're a real programming whiz, usually they require more time. So I'm assuming no one in here has ever programmed with assembly language. So that's going to be a whole new language for you. And on top of that, you're going to be modeling with Verilog, which is a whole nother software, which you do have some experience with. But as you've all experienced, I'm sure in 133, sometimes Vivado can be frustrating, right? Okay, so anyway, I just wanted to put that out there. Like I said, I'm an honest person. I'm just letting you know how it is. So this is the Canvas page for the course. I sent an email to everyone. Hopefully you've taken a look at this. I can go on Canvas and I can see like what students have accessed it, but I can't really tell like for how long, although sometimes it tells me how long a person has been on the Canvas. So I think just about everybody's looked at this. I don't plan to go through all of this unless you have specific questions about something, but I just wanted to point out a few things up here and also give you some highlights about the course that you can see written over on the left side of the board. First of all, there's this community website that the ISA, Derek, created. So it's like Slack, right? It's just a place where you can go and help each other and discuss the course and whatever else you want to talk about. Hopefully you've all read the course intro. The lab manual has all the activities. There's hardware activities where you're building that Otter microcomputer piece by piece, and there's also software activities where you're learning assembly language. And every week there's 2 assignments. You know, some weeks it's a software and a hardware assignment. Other weeks it's 2 hardware. Other weeks it's 2 softwares. It's just how the schedule is going. Now, as far as, oh, and also there's a textbook, Dr. Mealy's textbook, but it's just there for reference. Okay, what I have on Canvas and what I present in class, that's the most important information during the quarter. And then, like I said, there's hardware and software assignments. The criteria for what you submit for hardware is right here. You can just click on that and see what you need to submit, and same thing for the software. Okay. Under meetings, now, we lost another meeting. You know, before the rain, we lose a meeting due to the holiday next week. And as you know, we lost the last Tuesday due to the rain. So actually now we only have 18 meetings instead of 19. But I will make adjustments towards the end of the quarter when we get to the project. For example, I don't think we're gonna be able to build everything that's in that Otter diagram. I'll have to probably take something out because of the classes that we've lost. But anyway, there's also resources on the Otter, which is the name of that microcomputer. There's System Verilog, Stop, Xilinx, Vivado, and also the FPGA, the basis board. You won't really need the basis board until the end of the quarter. Okay, unlike 133, where just about every week, you're downloading something to the board and testing it out. In this class, as you build that microcomputer, you're simulating each piece, and then you don't really download it to the board until at the end when you have it all working together. Okay, so the basis board, you won't need to until towards the end of the quarter. Now, again, if you don't have your own basis board, we have basis boards in the back on the benches in the back. Now, everybody, I would think, hopefully, kept Vivado installed on their computer. Does everybody have Vivado on their computer? Okay, if you don't, that's something you definitely want to do real soon. Now, that's for modeling the hardware. And then there's also a software called RARS, which is a Java program that you're going to be using to see if your programming, your assembly language programs are working the way you want them to work. Okay, and there's links on Canvas for both Java and that RARS program. Okay. Now, by the way, if you have an old version of Vivado on your computer, that's fine. In fact, last quarter we found there was quite a few, or at least one major bug with the newest Vivado. I have version 20.1 on my computer, and it works fine for our needs. So if you have an old version of Vivado on your computer, I would just use it. Don't try to install something newer because it might be worse than what you already have. Okay. All right. So is there anything that was on Canvas that you have any question about? Which one? Both or just? I guess we're gonna go over both. Okay, sure. We can look at it. Let's see. We'll look at the software one first. Your first assignment. Okay, so for software assignments, there's basically 3 parts to what you submit. A flow chart, and I'm going to give you an example of a flow chart later in today's class. Then test cases, and then just show what your code is. I would say out of these 3, the one where there's the most probability of losing points is with the test cases, because unlike in 133, at least the way I taught 133. I would basically give my students the test cases, especially at the start of the quarter. As we moved along, I was less and less likely to give test cases. In this class, you're evaluated on if you can come up with appropriate test cases. And I'll talk more about that later.
And on this class, with the team member, will you bounce test cases? If you share test cases with your friends?
Yeah, in fact, all the lab work in here is group work. Okay, so I'm going to talk about that. So yeah, you'll be working with, in most cases, one other person. Okay, any other questions or comments on this here? Are you good? Hayden, is it? Yeah, okay. All right, so that's the software. And hardware is similar. Okay, because there's test cases for the hardware also. Again, I would say that's where historically anyway, some students have some struggles with. But structural design, you get that right from Vivado. That's just your elaborated design schematic, right? You just got to make sure that looks like what you intended. And then also providing your code. Now, what's really important, and I'm going to be saying this throughout the quarter, but let me say it for the first time. What's really important in this class that you could have gotten away with in 133 is that first, you have to be very descriptive with your inputs and outputs. For example, if you just label your inputs A, B, C, and your output F, let's say, you're going to run in, or you're likely to run into a whole lot of difficulty when you get to the end of the quarter and you're troubleshooting that Otter diagram. Okay, because you're going to have a timing diagram at the end of this quarter that's got like 50 signals, right? Where in CP133, maybe you had a design that had a dozen, you know, if you had something fairly complicated in that class. But here, the level of difficulty is probably tenfold, if not more than that. So, you know, for each of these blocks, you want to be descriptive with your inputs and outputs. You just don't want to label them A and B. You know, like maybe you label them PC for program counter, like PC in and PC out. And then for another block, like the reg file, you know, you have like reg file in, reg file, you know, you want to be descriptive with your input and output names. Okay, the other thing that's very important in this class that you could get away with in 133 is unintended latches. Okay, 133, you know, if you had a latch where it wasn't supposed to be, like you had some sort of combinational circuit, right? Not a memory type circuit, but a logic type circuit, and you made a mistake in your code that created a latch. Well, in 133, because the designs are fairly basic, it may have worked okay. Okay, that's not the case in this class. If you have any unintended latches in any of these blocks, in all probability, your odder is not going to work. Okay, so you have to keep an eye out for that, and I'll be constantly reminding you of that fact. Okay, but that's just a couple of things right from the start that's different in this class compared to your 133 class. Okay. All right, so any other questions about the criteria for the work that you submit? Everybody's good? Is there anything else on Canvas that you want to talk about? I mean, this isn't the only day we can talk about this. I'm just, you know, there's something today that you ran across when you were looking at it, you know, before today. Otherwise, I'm going to shut this down. So no questions? Turn this off here. All right, so let me just talk about some of the highlights of this class. I mean, I've mentioned a few, but let's just go through the list. First of all, as I had on Canvas under the course intro, this is what's called a blended class. The first 3/4 of the class, all the meetings are in person. The last couple of weeks, now I have online, but it's online in the sense that I'm available on Zoom to help you as you work through your projects. Okay, the last couple of weeks of the course, you're finishing up. You know, you'll have all the individual pieces, and in the last couple of weeks of the class, you're putting this all together, testing it, debugging it, and there will be debugging. And then hopefully, once you have it working, downloading to the basis board and then running a program. Now, in this class, attendance does matter. As you saw, in fact, let me mark off a couple of people that came in right at the beginning. Diego came in. Then, are you Emily? Okay, so we got everybody. So yeah, every day I take attendance. Now, if someone comes in late and it's just, you know, a few minutes late, that's all right. But if someone is consistently late, then I do start prorating. Okay, so anyway, attendance does matter, so you should be here on time. Now, the way the class is going to run is that roughly the first half of the class is a lecture. Now, today it's going to probably be longer. Today, probably the first couple of hours is going to be a lecture. Now, I'll take a break at some point. Okay, I don't expect you to listen to me for 120 minutes. But then once the lecture part is done, then you have in-class time to work on the assignment. Okay, like today, the assignment is a software assignment. You're going to be introduced into writing assembly language. Okay, and I'm going to give an example before you start the assignment. Like I mentioned, there's 2 assignments per week. Sometimes they're both software, sometimes they're both hardware, sometimes it's hardware software. The assignment that you start on Thursday is due the following Monday. Now, this assignment today, a little bit different because there's a holiday. As you know, Monday is Martin Luther King holiday. So I think instead of having it on Monday, I have it on Wednesday. Okay, but the rest of the quarter, whatever assignment you start on Thursday is due the following Monday. And then the Tuesday assignment is due on Friday that same week. Right, so every week there's 2 assignments. One is due Friday, the other one is due Monday. I do allow you to turn in assignments late up to 5 days. There's a 10% deduction per day. And because I accept late assignments, there's no extensions. And the only homework is to work on the assignments that you don't finish during class. In the lab work, both the software and hardware, it's group work. Okay, you'll be working in 2-person teams. Now, of course, if I have an odd number of students, if we end up with an odd number after add drop, you'll have to be a 3-person team. But it's mostly going to be 2-person teams, and each team does 1 submission. Okay, so there's 28 students in the class right now. So on Wednesday, I think of next week, when the submission for the assignment that you start today is due, there should be 14 submissions. Right? 14 groups, 14 submissions. Now, this is really important, okay, because I started doing this last quarter, 133, and for the most part, I think it worked out really well. I would say for 90 to 95% of the students, they followed this. What they followed was this here, okay? That even though you're submitting 1 submission for your group, each student is doing their own thing. Okay, they're working independently. Right? Now, what that means is, there's no looking over the shoulder, right? There's no like 1 computer with 2 people sitting at 1 computer. Also, and this is the thing I wasn't anticipating that happens less than 10% of the group. So this is only like 1 or 2 groups in each of my sections. And that's 2 people with their own computer sitting side by side, typing in the same thing. Okay, that's not working independently, right? And the only way I found out about this, I had no idea people would do that. I just thought they would know, hey, I'm doing my thing, you're doing your thing, hey, we can compare, learn from each other. The only way I found out about it is one of the students would call me over because they were having some difficulty. And I would look at it and I'd say, well, how about your partner? Oh, well, it's the same thing. You typed in the same thing. Well, that defeats the purpose. Right? So, just to make sure this doesn't happen, there's no side-by-side. Even if you have your own computer, there's no side-by-side. Either sit across from each other, or what some groups did last quarter is that, 1 person in the group sat here, the other person in the group sat over there. And they were working, and then if they ran into problems, they came over and they helped each other, okay? So, the idea of the group work is so you can learn from each other, but it's still doing your own thing. And then hopefully, by the time the assignment is due, you both have working designs and you can choose which ones to turn in. Some people like 1 week you turn this person in, and next week the other, whatever. Okay, you turn in the best one, what you consider to be the best one. Okay, there's also going to be a few activities, and people that were in my 133 class know what I mean by this. In 133, where there isn't as many assignments as there are in this class, what I would typically do every lecture is after I lectured, I would give an activity that was like a homework assignment almost before they started their design. Well, I can't have as many activities in this class because, again, there's just enough assignments as it is. But I'm still going to have a few activities. I think there's maybe 2 or 3 the whole quarter that just kind of prep you for that assignment. Gives you just a little added practice because those assignments are a little bit more, I think. I think you need a little practice before you actually start the assignment. Okay, it's just a call on my point. Other instructors don't do that, but okay, there's gonna be a few. And that's also these activities group, there'll probably be groups of 4 for this. I haven't totally decided yet, but it'll probably be groups of 4 for that. And then also, if you look at the syllabus, you already know this, there's a midterm and a final. The final is going to be online. And then there's the project that I talked about the last couple of weeks, which is group. And that may be a 4-person group for the hardware and a 2-person group for the software. That's what I'm leaning towards right now. All right, so any questions up to this point? Yeah, you need a basis board, but it's not till the very end. Like the last couple of weeks, once you have this put all together and it simulates all correctly together, then you'll download it to the board and see if it works on the board. Is it possible? Yeah. Yeah, we have, I think there's 8, 1 on each of the benches. Yeah, of course, the advantage of having your own is that, you don't have to rely on those being available. But other than that, it's the same. Okay.
For the online final, is it like over Zoom and you don't have to have like a classroom?
I haven't decided totally on the format yet, but I'm leaning towards that it's not going to be like on Zoom. It's just going to be something on Canvas that you have to be available at a certain time to take action. That's what I'm leaning towards. It's only great. Yeah, I'm because you have to do so much work during the quarter. I plan on the midterm and final being more like multiple choice type tests. They're not like high stress. Some people think multiple choice is high stress. I mean, I think it's all relative. But it's not going to be like a 3-hour final. It's not going to be like a long. Well, I think for the midterm it's still 60 minutes, but it's likely to be just multiple choice, fill in the blank type of questions. Okay. Any other questions? All right, tell you what, I've been talking for what, a half hour or so. Why don't we just take like a 5-minute break? And in 5 minutes, I'll just go over a little bit of review, and then we're going to start into the course. Okay, so come back at 1:15 if you leave the room. So, just a second. I just want to stop this. So, in 133, with the FPGA, you're modeling hardware. See, FPGAs, they don't run programs. It's not like a microprocessor, right? A microprocessor is circuitry that's going to be executing instructions of a program. FPGA is not that. It's not anything like that. Okay? All right. The next thing I wanted to go over that kind of pertains to what we're going to be doing today is just some basic definitions. You've all seen this term, right? A byte. Okay, what is a byte in logic? 8 bits. Okay, how about a word? Well, you can have a word, that represents a character. But in the general sense, in the logic world, what's a word? Like, is there a specific number of bits for a word? Like a byte is always 8 bits. Is a word always a certain number of bits? 65. Well, you can have like either a 16-bit or even a 16-bit word. See, a word represents how many bits that a particular piece of data is for a microprocessor. And usually the number of bits a word has is the same as the number of bits of the microprocessor, right? Because you've all heard of like, this is a 16-bit microprocessor, this is a 32-bit microprocessor, this is a 64-bit microprocessor. Do you know what determines the number of bits we say a microprocessor is? Like when we say a microprocessor is 32 bits, do you know what that means?
That's how much data the process.
Yeah, that's typically the length in bits of the data that it typically processes, which agrees with the number of bits that most of the registers inside the microprocessor can hold. So, you know, when you say you have a 32-bit microprocessor, that means that most of the registers within that microprocessor can hold 32 bits and that your data is 32 bits. And in this class, the Otter, it's a 32-bit microprocessor. So our words are 32 bits. Okay, but you could have another microprocessor that has 16-bit words or 64-bit words. Okay? All right, so that's what a word is. What do you think half a word is? If the word's 32 bits, right? 16 bits, right? For half. Okay, so you're going to see that in this class, words are 32 bits, well, bytes are always 8 bits, and half words are 16 bits.
Does the word refer to the string of bits that follows the curly bit? Is that what you think that word?
Right, yeah, you're going to see that for this Otter, the instructions are 32 bits. Yeah. Yeah. Okay, next thing. Remember 133, we had unsigned numbers and signed numbers, right? So if I have some 4-bit unsigned number, like what I just wrote on the board there, how do you figure out its value in base 10?
The most significant, the most significant bit is not assigned bits, and you just keep the highest.
Yeah, right. That's the key thing, right? When you have an unsigned binary number, all the bits have numerical value. There is no signed bit like there is with signed binary, right? That's a key point. So like you learned in 133, right? This least significant bit, that's your ones column, right? 2 to the 0, then 2 to the 1, 2 to the 2, 2 to the 3. And so how many ones, how many twos, how many fours, how many eights? So this would be 11, right? In base 10. Put a little subscript, right, to identify the base. Okay, but what if this is signed? And in 133, what was the most important signed format? Remember there was like 3 different formats? Oh, right, who's complement? Yeah, there's like signed magnitude and there's like ones complement, but the only reason we really even mention those in 133 is just to let you know there's other formats for, you know, negative signed binary numbers. So 2's complement is the most important one. And that's the one that the Otter uses. Okay, so 2's complement. So if we had 1, 0, 1, 1, and 2's complement, another way to identify 2's complement is RC, right, radix complement. So now what do we have? Instead of 11, like if we take it as an unsigned, what would we have if we take that as a signed 2's complement? Be negative what? Yeah, how did you get negative 5? Right, because now your most significant bit is the signed bit, right? That doesn't have numerical value. And at the 1, it just tells you it's negative. And to get the value of a 2's complement, when it's negative, you flip the bits and then add 1. Is that all coming back for people? How about This is something that people sometimes miss from 133. Then how about if I want to negate two's complement. Every time I put sign in this class, I mean two's complement. Like let's say you know, I have a binary 2, 4-bit binary 2. And I want to negate that. How do you negate any signed binary number?
I do the same process.
Yeah, exactly. Right. That goes back to, remember how there's two's complement the noun, and then there's two's complement the verb. Right? Two's complement the noun, that's just a list of two's complement numbers. Right? But two's complement the verb is when you take the two's complement of a signed number, whether it's positive or negative, it's going to negate it. So see, this is a positive 2, right, in base 10. And now if I flip the bits and add 1, right, I get this. And what is this in 2's complement? It's -2, right? The sign bit becomes a 1, which means it's negative. And now I flip the bits and add 1. Okay. So you see, if I take the 2's complement of a signed binary number, it negates it.
So you're saying that you negate the same value, you just sort of complementing it?
Yes. See, that's 2's complement the verb. See, that's what sometimes people miss in 133. Like they understand 2's complement the noun, like the first thing. But then they think 2's complement is something just for like a negative number, right? To get the value. But there's also 2's complement the verb, right? Here we're doing 2's complement on a positive number to make it negative. And if you take 2's complement of a negative number, it makes it positive. Okay? That's probably the most important thing in this review that has to do with your assignment that you're going to start later. Because in that assignment, you got to negate a binary value. How do you negate it? Take the 2's complement, flip the bits, add 1. Okay? Let's see, what else did I want to? Oh, the range of unsigned. Well, everybody okay before I go to the next thing? Okay, the next thing I just wanted to review is like the range depending on the number of bits you have. Let's start with unsigned. If I have unsigned, that's 4 bits. What's the range? What's the minimum value of an unsigned 4-bit number? Just be 0, right? Because you just have all zeros. Just be 0. Okay, what would be the high end of that range? 15, right? Because the high range is all 1, so 15. And let's say I had unsigned 5 bits. What would the range be? 0 to what? 31. Right. Everybody see that? Right, because if I have 5 ones, it would add up to 31 basically. So how could I write this in a general sense? I mean, clearly in a general sense, no matter how many bits I have, if it's unsigned, the minimum is going to be 0. But how could I write the max number in that range in a general sense based on the number of bits? Let's say n is the number of bits.
Is that 2 to the power of n?
Yeah, you got it, right? It'd be 2 to the n minus 1. Okay, well, in this class, as I said earlier, our data is 32 bits. So if we have an unsigned number and it's 32 bits, your max value is 2 to the 32 minus 1. That's a big number. Right, you can put it on your calculator and see what it is. It's like, I think like 4 trillion something. I don't know. It's a big number. Okay. All right. So everybody good with that? Okay. How about if we have a sine two's complement. And let's say it's 4 bits. What's the range for two's complement? What would the max range be? Right, the max range would be 0, 1, 1, 1. Again, this is the sine, right? So it'd be +7. And what would the low end be? This is where if people make a mistake, they usually make it here. What is it? Right, it's -8. What's -8 as a binary? What do I write? Right, 1, 0, 0, 0. See, remember that's the big advantage of two's complement over the other formats of negative binary numbers like sine magnitude and one's complement. Remember, sine magnitude and one's complement, they have 2 values for 0. Remember that? Like with those 2 formats, you have +0 and -0. And what is -0? Right? See, that's one of the advantages that two's complement has. You only have 1 value for 0. And you pick up another value in your range. Right? Because for sine magnitude and one's complement, your range would be -7 to +7. And see, two's complement, 1, 0, 0, 0, it's not -0, it's -8, right? Because you flip the bits at 1. Right? So how about, again, well, actually, let's do one more here. Let's do 5 bits. 5 bits would be what to what? That'd be -16 to +15, right? Okay, so how could we do a general? Using n for the number of bits.
So it would be 2 to the power of n minus 1 plus 1, or the negative bit or minus, and then 2 to the power of n minus 1 minus 1.
Right, yeah, because this is going to be no different than what we have for the unsigned, right? The max one, that's still going to be, oh, actually, no, it'd be different because we got to subtract 1, don't we? Like you said. Yeah, so it'd be 2 n to the -1, then -1, right? Did I do that right?
Yeah, for the positive.
To the positive. Okay, and then what would be the simplest way to do the negative one? It would just be 2 to the n minus 1 and what else? Put a negative in front, right? Everybody agree with that? Well, this is plus, right? There's a negative here. Right, to say it's 4 bits would be 2 to the 3 minus 8. Yeah. Again, your otter 32 bits. So a 2's complement number, the otter, it'd be minus 2 to the 31. 2 to the 31 minus 1. Again, a big number. It's like 2 trillion something. Okay? All right, so is this erasing any cobwebs from 133? It should be familiar. Maybe you haven't done it in a while, but you're probably like, oh yeah, it's starting to come back. Okay, so like I said, in future lectures, I'll do review, fitting for that particular assignment coming up. But this is pretty much what you need for the assignment you're going to be starting today. Okay, that comes from 133 anyway. Okay, so let's go ahead and move on. And let's start talking about the otter. Well, as I mentioned, the otter is a 32-bit microprocessor. Now, you'll also hear people call it a microcomputer. There may be other people that call it a microcontroller. See, there's these 3 terms: microprocessor, microcomputer, microcontroller. And people use those terms interchangeably as though they're all the same thing. But there's technical differences between the three. But even people in the know will often use them interchangeably. Okay, and in this class, it's not incorrect to call it a microprocessor or a microcomputer, or even if you called it a microcontroller, although that one's stretching it a little bit, I guess. But in case you're interested, the technical differences between the three are a microprocessor. Like if you have a microprocessor IC, it just has all the logic circuitry, which is mainly registers, that a microprocessor entails, and it has no internal memory. A microcomputer chip has everything the microprocessor has, along with onboard memory. And that's really what we have here with the Otter. And then the only difference between a microcontroller and a microcomputer is how the memory is used. A microcontroller will mainly be using memory for I/O devices. Like it's controlling a lot of peripheries. It has a lot of sensors. Okay, so that's really the difference between the three terms. But in this class, MCU or microprocessor or the Otter is fine. Again, we call it a microcontroller. It's kind of stretching it because it all depends on how you're using it. But the key thing is that this Otter runs programs. Right? It's going to be executing instructions, okay, which an FPGA, like we talked about earlier, does not do. Right? That's the fundamental difference between what you're doing in 133 and what you're going to be doing with this Otter, right? The FPGA is modeling hardware, and again, you're going to be using that to model that Otter, but then the Otter is going to run on assembly language executing instructions. That's what makes it a microprocessor. Okay. Now, microprocessors have specific hardware. But when I say specific, a better word is non-configurable. See, again, unlike the FPGA, right? Because the FPGA has all these different logic blocks that you can configure different ways based on the code that you write in Verilog. Okay, a microprocessor is not like that. The Otter, this is its hardware. And if you have some other microprocessor, it's going to be different hardware. And each microprocessor has unique instructions. Okay, they're called ISAs. Okay, so like an Intel processor is going to have a different set of instructions than a Motorola processor is going to have, than what this Otter has. Now, this is hardware. Now, the Otter's instructions is a RISC-V instruction. And the main thing about RISC-V is that it's an open source. So, they come up with these instructions, and Dr. Kalinas, Dr. Hummel, Dr. Mealy, and also Dr. Benson, they all worked together and came up with this Otter processor along with the instruction set. So, they took the open source RISC-V and they suited it to this hardware. See, one of the things that you're going to learn in this class, if you already haven't run across it, is that microprocessors, the software and the hardware, it's all like intermingled. You can't learn about the hardware of a microprocessor without knowing its instruction set. And you can't really know what the instruction set is doing unless you have some idea of how the hardware is working. See, they're all intermingled. And, that's why in this class, sometimes you'll have a software assignment, sometimes you'll have a hardware assignment in the same week. right? It's not like this class could be taught where you only do hardware for say like 4 weeks and then you only do software. I mean, I suppose you could try doing that, but it wouldn't be the optimum way of learning, right? Because by mixing it up, so to speak, hopefully you really start to see how the two are intermingled. Okay. Now the otter has approximately, don't hold me to this, but it's close. It has approximately 32 what are called real instructions. Okay, so what do we mean by real in this case? Well, what we mean by real, these are the instructions executed by the otter. There are also what are called pseudo instructions. In fact, one of the handouts or one of the pages in the handouts that you all have, this one right here, it's page 14. And this page came out of the assembler manual that's on Canvas. So this shows, it's a brief listing as it's written there. This shows the real instructions along with the pseudo instructions. The pseudo instructions are shaded. So the non-shaded, those are real instructions. Those are the instructions that the microprocessor actually executes. See, the purpose of pseudo instructions is just readability. Pseudo instructions are made up of multiple real instructions, usually a couple. You know, like most pseudo instructions are a combination of 2 or 3 real instructions. So just to show you how this fits into the hierarchy of languages is that, you know, you all have learned at least one high-level language, right? I guess most people Python. But, you know, Python, C, back when I was undergrad, it was Fortran. Those are all what are referred to as high-level languages. And then what the hardware actually executes are ones and zeros called machine language. And in between your high-level language and machine language, that's assembly. Right? So that's what you're going to be doing in this class. That's the RISC-V that you're going to be learning. Now, I just mentioned about a manual that's on Canvas. Now, you don't have to do this. You know, you can just look at it on Canvas. You don't have to print it out, but I printed it out. And you see, for each instruction that's on this listing, no, that's my notes. But that page 14 that we were just looking at a moment ago, right? This page right here. Every real instruction on this page has a detailed description of what it does. All right. Don't worry if you can't see all of this where you're sitting. I'm just doing this for more an overview effect. So like this first block right here is one instruction that's add. And then you got another instruction that's add I. And you see each one of these instructions, and, you know, this is page 18 that goes to page 50. So for pages 18 to 50, they're just instructions with a detailed description of what they do. And as part of the detailed description, they each have an instruction format that shows you the machine code for that instruction, the ones and zeros for that instruction. And each instruction is 32 bits. So you feel like this add instruction has a 32-bit machine code. ADI has a 32-bit machine code, all of these. Okay, so, when you took a high-level language, you probably learned that there's a device called a compiler that takes your, syntax that you write in high level and converts it down to the ones and zeros. Do they still teach that in high level? Do they talk about a compiler? Well, with assembly language, it's called an assembler. An assembler will take what you write in assembly and convert it down to the ones and zeros. Okay? So you see, assembly is closer to the hardware. Like when you look at an assembly instruction, it's going to have registers as part of that instruction. Like for example, when you add, okay, when you use the add instruction, it's going to add what's in register 1 to what's in register 2, and then output the result to a destination register. Okay, and many of the instructions are like that. They're very like register specific. Okay, now they're not all that way. You'll see that there's some differences, but in some way or another, each instruction will use a register. And a key part of the hardware that we're going to talk about in more detail later on is a piece of hardware called the reg file. If you look at your diagram there, you'll see a block that's labeled reg file. And that reg file contains 32 32-bit registers. And on this page of the handout that you have, okay, the one that is at the top, it has RISC-V auto registers. These are the registers inside that reg file. So you have a register X0, and then you can see it has an alternate name 0, X1 with an alternate name, and so on. Now, for this first portion of the class, we're not going to use registers 0 through 4. Okay, those are what are called specialty registers that have special purposes that we're not going to get to. Well, actually, we'll get to register 0 pretty soon, but the other 4, 1 through 4, we're not going to get to for a while. So when you do your software assignments, especially this first one, don't use the alternate names. Just use X5, X6. You can use X5 through X31. Okay, any of those registers you can use, for your first few assignments. Okay, and as we go through the course, we'll talk more about those specialty registers. Okay, so let's see, where are we at here? We went over all of this. Do you have any questions at this point? By the way, when you have a question, just yell it out. You don't have to wait for me to ask if there's questions, but I think, let's see, where are we at? Okay, the next thing is talking about how the memory is organized. But before I start talking about how the memory is organized, everybody, now, a lot of today's class, especially this about hardware and software, is kind of general. We're going to get more specific as we go along. Like, you're going to build this in a few classes. And when you build this reg file, we'll talk about it in more detail. But this is just some of the highlights at this point. Oh, question over here. Yeah, but right now, don't use for your software assignment, don't use registers 0 through 4, use registers 5 through 31. And most of the assignments, you're not going to need that many registers at the beginning anyway. So, if you use like 5, 6, 7, 8, 9 or something, it'll be fine. Yeah, I'm going to give an example of a assembly language program coming up here. Any other questions? Okay, so the next thing to talk about is how the memory is organized for the otter. And the Otter has what's called 32-bit address space. Okay, which means we have 32-bit words. And this is real key. The 32-bit words are byte addressable. Okay, so what I have drawn here is just how you can think of how this memory is organized. Now, each 32-bit word, or actually, let me phrase it this way. Okay, the Otter memory has 32-bit addresses. Okay, so whether the address is for a word or whether the address is for a byte, they're 32 bits. So that means our lowest address. Okay, now does everybody know what this symbology means when you put a 0 in X? What does that tell us about what's going to follow? Typically see this in timing diagrams in 133. What does it mean?
That's X.
Yeah, that what follows is hex. So your lowest address would be 0. And since it's 32 bits, how many hex characters are we going to have? This is also reviewed. I have 32 bits. How many hex characters does it take to represent 32 bits? What if we had 8 bits? Like, what if I had this binary number here? Do you remember how you can quickly go from base 2 to base 16? Break it up into groups of 4, starting with the least significant bit, right? So if I quickly want to go from base 2 to base 16, I look at each of these 4-bit groups and write it as a hex character. The 1101, what would that be in hex? C. Almost. No, we get further away. D. D. Why is it D? What's 1101 in base 10? 13. And 13 is D in hex, right? C is 12. Yeah. Okay, how about now I do the same thing to this group of 4. 5. Okay. Yeah, actually, I probably should have reviewed this at the beginning. Yeah, you're going to be doing this a lot in this class. Going from base 2 to base 16, right? This is the quick way to do it, right? You group in 4 and then write each binary grouping as a hex character. So getting back to my question, 8 bits, it took 2 hex characters, right? What was 32 bits? How many characters, hex characters would we need? 8. Characters. I don't know if I spoke that right, but it's good enough. So my lowest address would be just 4 zeros in hex, right? Which corresponds to 32 bits equaling 0. Now, one thing that I'm going to do here that you might not have seen in 133 is I'm going to do this. I'm going to put an underscore. The only reason I put the underscore there is for readability. Okay, the underscore, I couldn't have wrote all 8 zeros all close together, but just so because when you write them all close together, it's easy maybe just to write 7 instead of 8, So this is just to make sure, right? 4 on each side that I get the right number. Okay, and then what would be the largest address in hex? they're all S, right? Because that would correspond to 32 ones. Okay. All right, so everybody see what I did here? Everybody remember this? Okay, so now let's get back to how this memory is organized. So each rectangle here is 32 bits. See, 32 bits, 32 bits, 32 bits. And then I've got it separated into 4, like each row separated into 4 because each rectangle within a row would be a byte. Right? There's 8 bits in each of these, and there's 4 of them, so again, 32 bits. So each byte has an address. So this byte would have address 0, 0, 0, 0, 0, right? This byte would have address 0, 0, 0, 0, 0, 0, 1. This byte, I'm not going to keep writing the 4 leading zeros, okay? I'll just write the last 4 characters. Okay. Oh, and this is all in hex again. Okay, so what do I do here? Address 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, right? Because it's hex, so A is 10. Okay, what do I do here? I went C for 12, D for 13, E for 14, F for 15. So what would this one be in hex? What's after 0, 0, 0, F in hex? 0, 0, 1, 0. Right, because this column is how many 16s, right? So I went from 15 to 16, so that's why it's 0, 0, 1, 0. And you might have to review your hex. And this be 0, 0, 1, 1, 0, 0, 1, 2, 0, 0, 1, 3. Oops. And 1. All right, you getting the idea? You want me to keep going? Right, this would be 0, 0, 1, 4, right? Because that's 20. 16 plus 4 is 20. Okay. All right, so see, each byte has its own address, and then these addresses right here. Okay, this address of 0, this address of 4, this address of 8, this address of C, which is 12, this address of 10, which is 16, and this 14 here, which is address 20. These are the word addresses. Does it make sense that the word addresses are delineated by 4? Because how many bits is a word? 32. And how many bytes in 32 bits? 4. So you see, that's why the word addresses are separated by 4, right? Because we have 32-bit words, and each byte has an address, right? And bytes are 8 bits. Okay? You're going to see where this comes into play is that when the instructions are being executed by the microprocessor, each instruction is a word. So as the microprocessor is executing a program, it's got to have some device, and you're going to see the device is called a program counter, which steps through the program in steps of 4. That after one instruction is executed, it will increase the address by 4 to get the next instruction. Right? Because each instruction is going to be separated by 4 in address, right? Because each instruction is 32 bits. And memory is byte addressable. Did you have a question?
Yeah, how many of those blocks? are there?
Oh, total?
Right.
Oh. Well, how big is this number? Right? You could do what we did earlier with the range, right? We could find what this top address is by doing, what would it be? Be 2 to the 32 minus 1.
Okay, I guess my question, they're all organized in those 32 bit.
Yeah, each one of these, rectangles is 32 bits. But within each 32 bits, I have 4 addresses, right? Because each byte has an address.
I'm still not understanding. You're saying each little rectangle has 32 bits. in it.
No.
How does each one have 4 addresses?
Now, this whole thing has 32 bits. This has 8 bits, this has 8 bits, this has 8 bits, this has 8 bits. Yeah.
But you said each rectangle had 30 individual.
Oh, I'm sorry. Yeah, I meant this by
So the
rectangle.
row,
The whole thing I meant by rectangle. And then these, you can think of these like squares within the rectangle, maybe.
okay.
Yeah.
So
Sorry.
each row has 32 bits.
Yes. Yeah, sorry for the confusion. Yeah. Yeah, please ask. If I'm not clear, please ask.
Okay, so then how long is one address?
Well, the address is always 32 bits.
So the whole row is an address or one square?
Well, each square has an address. Okay, and each square is a byte. But if I want to address a word, which is 32 bits, which is equal to 4 bytes, right? Then I have to use these addresses here. So that's where the difference in 4 comes in. It's when I'm addressing 32 bits. See, I would only use this address or this address or this address or this address. Well, actually, I would only use this address, this address, this address for a byte. I could use this address for just a byte, but if I want to use all 32 bits, I have to use this address here. Now, you'll see when we get to look at the instruction, how this ties into the instruction. Okay, but for right now, this is just how the memory is organized. I think I saw his hand first. If you're,
Oh, okay. So each row is a word or?
right. Each row is a word, a 32-bit word.
Okay, so what's the significance of the far right rectangle of each row? That's just the,
Well, we have a byte here. Like all these squares, there's a byte.
right,
In each square where there's a byte has an address.
right.
But if I want to address a word, I would have to use these addresses here.
To signify that's like the end address. Of the-
Sort of, yeah, you can think of it that way, yeah. Again, I think this will make more sense when we get to the software, all right? Because then you'll see how the software ties in. But this is how it's organized. Okay, the way it's organized is each byte has an address, and then these are the word addresses.
So that, the word address, is that by design? Is that
Yes.
specific to this microphone?
Actually, right, actually, great question. That was the next thing I was gonna say, is that this is all based on the programmer. The programmer decides this. You know, these registers are just registers. You know, like what you learned in 133, right? Registers are made out of flip-flops, you know, most commonly D flip-flops, right? And they're just a collection of registers. So, you know, this is all registers. It's just the designer, the programmer who decides how those registers are going to be used. And if you look at this page that's on that handout that you all have, see, this shows how the memory is what we call segmented. Okay, that. You know, and again, I could have, you know, I've had enough time in my lifetime, right? I could I could draw, this many rectangles, right, rows, right, but life's too short, right? But it's also the programmer that decides how all those registers in memory are going to be what's called segmented. Like from addresses 0 to 5 FFF, that's where the instructions go. That's what's meant by the code segment. From addresses 6000 and hex to EFFF, that's where the data is going to go. And then you get something called the stack. Okay, we're going to talk about the stack, not for several more weeks. Okay, then you have something, and this is important for what you're going to be doing in the assignment coming up, is from addresses. Actually, and there's a typo on this page here that I need to tell you about. This isn't exactly correct. Yeah, make this note here. That MMIO, okay, what this stands for is memory map IO. IO is just input output.
Are these ones keep or you?
Yes. Yeah, I brought those for you to keep, but they're on Canvas too. But yeah, I just thought it would be easier this first class for you to look at it instead of looking at it on your computer. Okay, so MMIO, it stands for memory mapped IO. IO is just input output. Okay, but the note to make is that this segment of memory, it goes from address 110000 to 1100 and then you have another reserved section. That's the rest of it. That goes 1100. So the short of it is that memory mapped IO, it doesn't go all the way up to all Fs. There's a reserved section that's above memory mapped IO. And again, that was all decided by the doctors that developed the Otter along with the instruction set, Dr. Kalinas, Hummel. Those are the people that decided this. Okay. Now, what we mean by memory mapped IO is that all input output devices, input devices like switches or buttons, like on your basis board, and all output devices like LEDs and 7-segment displays on your basis board, they're identified by an address. Okay, so that's what this means. IO devices, ID. Right? The microprocessor knows those peripherals, if you will, by an address. That's how you identify it. Okay, you'll see that in your assignment that you'll be working on, the switches have a particular address. The LEDs have a particular address. And that's true for any IO. Okay, it's been about an hour since we had a break. So why don't we take another 5-minute break? And when you come back from the 5-minute break, I will do an example that will help you do the first assignment, which is, again, intro to assembly. Okay?
It's just, no, it's the avoidance.
Might as well, I had time. You can't. Oh, they also say, this hair and ID. Oh, it's like.
That's right.
I get you. At least I assume. Yeah. JP.
No, I'm taking over on this.
Plus, yeah, get songs of like the. But like the batteries change. So like I either keep it, I either and hopefully the battery stays in there, like keep it, but like I think it's better. They're doing the version. And that they give, I have to make sure that my data work.
It has to be.
I have to do it.
Better get us.
Then it is.
Yeah.
So
Yeah.
I just it's like a dog.
Okay, so let's go ahead and start up again. So when you look at the first assignment, okay, the number one software assignment, it has two parts. And we're gonna go through the first part together. And then the second part, that's what you'll do, you know, your two-person team, that's what's due. I guess it's Wednesday of next week, because again, because Monday's a holiday. So I wrote the problem statement for software number one, part one up here. Okay, it's to read three 16-bit unsigned values consecutively from switches. And look, the switches have an address. There should be a parenthesis sign here. So the switches have address 11000000 and X. So if you look at the range of memory map IO, right, that's its lowest address. So you see that's where the switches are at. Okay, that's how the switches are identified, by that address. So we're going to take three consecutive 16-bit unsigned values from the switches. We're going to add them together, and then we're going to output the result to LEDs. And here's the address for the LEDs. See, it's again in hex 11000020. Okay. Again, all I/O devices are identified by addresses. That's what memory mapped I/O means. Okay. All right. So anytime you're doing a software assignment, whether it's an assembly or any other language for that matter, where do you always start? What do you always start with? What diagram? A flow chart. Okay, and it's no different here. Now, on Canvas, and by the way, I don't think I mentioned this at the beginning. On Canvas, I do have, basically my notes for the class, I put them on Canvas. I mean, it's not 100% what my notes are, but most of it is there. Okay, so if you miss something, you can always look on Canvas to see what you missed. And on Canvas, it shows you the different symbols for flowchart, and there's some differences. I don't think they're all standardized, but I'm going to show you, what we use in this class. Okay, so, in any flowchart, you want to show where it starts. So we just use a circle. Okay, and then here we're going to be reading switches, and we're going to use this symbol here for either input or output. So, you can put like read switches. And we're going to do that 3 consecutive times. Okay, so we're going to read in switches 3 times consecutively. Then we're going to add those together. And for process, we just use a square. So you can just do that. And then the last thing is just to output it to LEDs. And then you just show where it ends. Okay, so any questions on the flow chart? I mean, you've done flow charts, right? I assume everybody did a flow chart in their high level. I don't know, do you use the same symbols? Like inputs and outputs have this, what's that, polygram, or I don't know what it's called. And then processes are squares, and then you just show the start and the end with the circle. Okay, well, one thing, before I show you the code, right, because once you have your flow chart, then you can go and write your assembly code. But before I do that, there's one thing I forgot to go over when we were going over the review of 133. And that's what you would add to either an unsigned binary number or a signed 2's complement binary number to not change the value. Like, for example, if I have this 4-bit unsigned binary number, right, 1011, which we said earlier is 11 in base 10. If I want to turn this into a 12-bit binary number and not change the value, what would I do? Yeah, just add zeros to the left of the most significant bit, right? Because of course, if I add zeros, 4, 6, 7, right? I'm not going to change the value. Okay. In assembly language, when this is done, when you take an unsigned number and extend it to more bits, we say that you're padding it with zeros. Okay, so like when you look at your instruction, right, your in your manual, your assembly manual, when you look at the detailed description of your instruction, a lot of times you're going to see it for an unsigned command, a command that's using values that are unsigned. You're going to see that it's padding to zeros to 12 bits or padding to 0 to 20 bits. That's what it means. It's just putting zeros in front of whatever number of bits you have, so it doesn't change the value. Okay, and it doesn't matter whether this most significant bit here is a 1 or a 0 if it's unsigned. It's just going to get 0. Okay, so that makes sense to everybody. Okay, how about if it's a signed 2's complement number? Say it's 4 bits. Say it's this 4 bits here, which you told me earlier was -5, right, in base 10. What if I wanted to extend this to 12 bits? What would I do so I don't change the value? Right, exactly. Because this is the signed bit, I would just extend with that same value sign bit, right? So in the case of taking this 4-bit two's complement sign to 12 bits, I would just add 8 ones in front of it. Right? If this was a positive two's complement number with a sign bit with 0, well, then I would add 8 zeros in front of it. Right? Does everybody see why? Because if this is a two's complement, this is a 1, when I go to get the value, I'm going to flip all these, right? Right? If I made these zeros in front of that negative sign bit, that would change the value, right? Because all the zeros would get flipped. That's something completely different. Okay, so this is called, when this is done in assembly language, this is called sign extension. Okay, so when it's a unsigned number and you add more bits, you're padding with zeros. When it's a signed number and you're adding more bits, you're doing sign extension, right? Because you're taking the sign bit and extending it. Right, does that make sense? Okay. All right, so now we can actually go back to this example here, and I'll show you the assembly that you would need to do this flow chart. Okay, so the first thing we're going to do is we're going to read switches. And in order to read switches, what we'll have to do is we have to put that address. Okay, this address right here, the switches, we have to put that into a register. Okay, and you'll see why we have to, but this is typically what you have to do in assembly. Okay, because any processing that takes place has to take place in register. So the command you would use is this LI, okay, which stands for load immediate. Load is the same thing as read. And when you're getting data, like here, we're getting data from switches. That's what's meant by load or read. It means the same thing. We're getting the data. Okay, now in this command, LI, like I said, stands for load immediate. The next thing is you put the register where you want the immediate to go. Now, I stands for immediate. And I don't know why this is so. I actually asked Dr. Hummel this because in this class, this is the first I've ever heard of this term immediate. And all immediate means in assembly language is that it's a constant. You know, a number, a value. Okay, anyway, I don't know why they choose immediate. It makes it sound like something it's not. Okay, but load immediate is just, the immediate is just a number. So we want to load a number into register 5. So in this command, you put LI, right, the instruction, you put the register where you want to put the number. And then here, the number is the address. So we just put our, now when you type this into RARs, okay, because RARs is the software where you test to see if your assembly language program is working, you don't put a hyphen or you don't put an underscore. Right, again, that underscore is just for readability, but RARs will freak out if you put an underscore. So you do have to just put it like I did here. Okay, so see, I'm going to skip over this flow chart. Now, in RARs, when you make a comment, you put the number sign, and then anything after that number sign is the comment. So this command here puts switch address in register X5. And like I said earlier, you can use any register 5 through 31. So, you know, you can use any register 5 through 31. I just happen to use 5, but this will work no matter what register you choose. Okay? All right, the next thing we're going to do is we're going to do what's called a load half word unsigned.
We only use the X5.
Say that again, please.
We only do the X5 for the 31.
No, you can use any register X5 through 31.
X5.
But I just arbitrarily chose X5. You could use any of those registers.
And then, so the register address is only X5, so that's 1 bit.
Well, no, remember, all these registers are 32 bits. So I'm putting this 32-bit number, which is the address for the switches, I'm putting it into a 32-bit register X5.
I just don't get why we just have X5, that should disable it.
Why we just have X5?
Well, we put X5, but that's only 5. And 1 there for 1 byte.
No,
Or is
X5 X5 is a 32-bit register that's in the reg file. Like this page right here with these registers, these are all 32-bit registers.
So the register, I'm sorry, the register name have an X for the.
Oh,
register name.
that X5 doesn't mean text.
Okay.
Yeah, the X in front of the register name doesn't mean hex. I don't know why they put an X there, but they did.
So X, it only means X if there was a 0X.
Well, yeah, I mean, in timing diagrams and also like our addresses, yeah, if it's a 0X, it means hex.
Okay, so the register name refers to an address, and it does that automatically.
Yeah. Yeah, well, let me rephrase that. I mean, you're gonna see how this reg file works in a few classes.
Okay. So,
Yeah.
Okay.
Yeah. Okay, any other questions? Everybody okay with this first instruction? Again, this first instruction, it's just putting this value, that's the address of the switches, it's just putting it into a register. And I just chose X5, but you could have done X6, X7, X31. Okay. All right, so now the next command is we're going to do, this is a load half word unsigned. So what is a half word in this case? How many bits? 16 bits, right? Because again, a word is 32 bits. See, we're using, if you look at the instruction set, right, that instruction set, you'll see there's also a load word. There's also a load byte. Okay, but we're using load half word because in the statement, we're getting 16 bits, right, which is half of 32. And then also there's a load half word without the U, and there's the load half word with the U, right? The U means unsigned. So since we're treating that data from the switches as unsigned, that's why we put a unit. If we were treating it as signed, we would use the command LH, load half word, because if it's load half word, it treats the data like a 2's complement. And the only difference between the two is how you extend the bits, right? If it's an unsigned, it's going to extend the bits by padding with zeros. If it's a signed, it's going to do sign extension to get more bits. See, that's the only difference between the two commands.
That's already there.
Right, right. Yeah, you're going to see where it's done later on, because you'll see what block does it. Okay, but for right now, that's the reason why we're using this, right? We have, because 16 bits unsigned, that's how we're treating the data. Okay, then the next thing that comes in this command is the register that I'm going to put the data in, which I chose to be register 6. Okay, and then we're going to have this, and I'll explain what this means in just a second. And what we're doing here is we're reading data from switches. All right, so what we have here is that what this instruction is going to do is that it's going to take the data from the switches at this address and put it into register 6. Now you see how there's a 0 in front of the X5 here? That's an offset. Okay, you'll see the purpose of this in a minute. But what the microprocessor does is that it adds this offset to what's inside the parentheses. So since I made it 0, it's just going to take this address that I put into register 5 and use that address to get the data from the switches and put it into register 6. Does that make sense to everybody? Okay, well, I'm just gonna do this 3 more times, right? Because I want to read the switches consecutively 3 times. So I'll do another load half word unsigned, but now I'm gonna put that data into register 7. Right, and then I'll do it a 3rd time, and I'll put it in register 8. Okay, so at this point, I've got 3 sets of data from the switches in 3 different registers, right? X6, X7, X8. Now I'm going to add them, right? Because that's what we want to do, right? We read in the switches. Now we want to add those 3 values together. So there's an add command. Oh, I forgot to put commas here. There's a comma after here, comma after here, comma after here, comma after here. Sorry about that. So now I'm going to add. So what this add command does, it takes the contents of these 2 registers, adds them together, and puts the result in this register. So you see, after this command, I'm going to have X6 contents plus X7 contents in register 9. Okay, so then I'm going to do another add. Okay, so I added content 6 and 7, put it in 9. So now I'm going to take those 2 added together, add it to 8, and get my final result in register 10. Right, so in register 10, at this point, I'll have the 3 added together.
Would it have mattered if, for example, you did X9, comma, and then X7, comma, X6?
No, because it doesn't matter what order these 2 are.
This is the first of the 3, like
Yeah.
X9 and X10 first.
Yeah, whatever you put here, it's going to add those 2 and put the result here. Now, there's also a subtract command. You know, in the subtract command, it would matter like what order these are in, because I'd have to look at the details, but it's either this one minus that one or that one minus that one, right? So if it was subtraction, because there is a subtract command, then this would matter.
Yeah.
But since we're adding, it doesn't matter.
Oh, is there no way to add on?
No, it's not. There's not an instruction that would like add 3 registers. Yeah, we don't have that. So yeah, we have to do it in 2 steps. Yeah. That's a good question. Now, if there was, it would be easier, but yeah. Now, there could be. Now, actually, see, your question brings up another good point. Because like we said earlier, each microprocessor has its own unique instruction set. So there could be a microprocessor, I know, there could be that does have that instruction. But its hardware would be different. Okay, so then we've accomplished this. So the last thing to do is output to the LEDs, right? Output the result to the LEDs. So to output, it's a store command. Okay, this is store. Yes. See, store half word. And store is the same as write. And load is the same as read, store is the same as write. So we're going to store the half word. So this is the data that we want to write, and we want to write it to the LED. So this is where the offset comes in. Remember I said earlier in these load commands that this 0 before the parentheses where the register is that has this address is an offset, that it just takes this and add it to that, and then it uses that as the address. Well, this is where it's useful, because now here in my store instruction, because the address for the LEDs is just 20 hex from the address of the switches, what I can do is just this. Right, because register 5 still has this address of the switches. So this is just going to add 20 to it, 20 to this, which gives me the address of the LEDs. And now this instruction, it's gonna take the result that's in register 10 and it's gonna output it to the LEDs. Okay. So, if you understood what we did with this example, then the second part of this, you should be able to do, because the second part of this, if I can find where my, let's see, where is it? I think it's right here. Okay, so your assignment is just to do the second part, because we did the first part in class. Okay, so the second part, read an input from switches, right? Same address. Assume the input is 16-bit signed in 2's complement. Change the sign of the input and then output the results to the LED. Okay, it's actually less instructions than what this one was.
Can you go over the, so, one of them you have an O, and then you have OX, and then one, if you just have an O, what's the, it's just like talking that between, having one O and specifying OX.
Okay, yeah, so, yeah, listen up, this is important. So in these load commands and also the store command, you'll have a number in front of the parentheses. Whatever this number is, it's gonna add it to what's inside the parentheses before it uses it for the load. So the reason I put a 0 here is because I want to load from this address, because I put in the address for the switches. So I don't want to add anything to it because it's already the address I want. So that's why I put a 0 there. But now when we get down to the store where I want to write to the LEDs, because the address of the LEDs is 20 hex from the address of the switches, that's why I put a 20 here, because it's going to take this 20, add it to this, and then do the store.
So why do you put the 0?
Because in the command, you got to put a number here.
Oh, you're not.
Like if you don't put a number there, I don't know what will happen. It'll just be like a unknown or something. I mean, I think in RARs, it would probably shoot out an error, you know, that it wasn't complete.
For load commands, you have to put a number.
Yeah, you would have to put a number in front of here. Otherwise, it wouldn't know what to use as the offset.
Oh.
I mean, I've never tried it. I mean, when you go into RARs, because, you know, you'll be inputting this program that you write into RARs, and there's a video on Canvas where I show you, okay, I show you how to input a program into RARs, and I show you how you check it to see if it works, because you'll see in RARs, you can step through the program instruction at a time. So you can look at what effect this instruction had. Like part of RARs, it shows you what the contents of the registers are. So when you step through RARs and you get to this instruction, it should show that this number is going in register 5. Like you'll be able to look and see if that happens or not. And then for this instruction, you should see the data at this address go into register 6. Okay, so you'll be able to step through and see if your program's working the way you want it to using the RARs program.
And one last question, just to make sure I'm saying what offset is. Could you add an offset to a number, like a simple one? I'm not really sure if you're increasing the number of bits, or you're just increasing the address. Do you read it from there?
Right, because I put an address into this register 5, whatever number I put here, it's going to add it to this.
Oh, okay, so you're reading another spot.
Yeah.
Okay.
Yeah, see, the reason they do it that way is because it makes it convenient in a case like this where, you know, you got an input at a certain address, you're going to output another address, and you can just use the offset to change, you know, where the data is going. It actually saves commands. It's a more efficient way of doing it, actually.
And so OX20 adds 20 in X.
Yes.
Okay.
Yeah, because this is in hex. Yeah.
Okay, cool. Thank you.
Okay. Another question here?
So how do we know what the final result is? Like what's stored?
Well, that's where the test cases come in, right? That, you know, you're gonna wanna put, you'll see, again, if you watch the video that shows you how to use RARs, it will show you how to put the data in for the switches, like you'll put the data for the switches in that memory location. Right in there.
It's in the video.
Yeah. Yeah, in the video, I show you how to use RARs, I show you how to, put the data for the switches, I also show that you can check to make sure that the result went where it should. Yeah. So yeah, if you watch that video, if you still have questions, let me know. But I think you'll answer it. Okay, any other questions?
Yeah, so in the first command, you are reading in the address for the switches,
Yeah.
and then you're using that register X5 in the next command. Could you just use the same address for the switches
Well,
instead of X5?
because I put a 0 there, I am using this address.
Sure, but I'm saying, yeah, I know that's easier, but would it be the same thing? to Just use the address for the switches in those.
I
three
don't
commands?
think there's a command like that in this instruction set.
Okay, so you need to use another register.
Oh, okay, you're saying, yeah, for these, you want to put each switch data into a separate register, yeah, because if you didn't, like, if you had X6 here, this would just write over what you had
Right.
previous.
That's not my question. So the second part of the LHU commands, all three, you have 0x5.
Right.
If instead of 0x5, you had the address for the switches, just written out, right, 0x11000000, would it accomplish the same thing?
No, because these instructions have formats,
Okay,
yeah, like syntax, you would like violate the syntax.
okay, so you need to use registers for those.
Right. Yeah, anything you're doing, like any sort of operation, whether you're adding, subtracting, anding, oring, it has to take place inside a register. Like you have to put the data there first to do anything with it.
Okay, so for that final address for output info, so that's only 8-bit output. Okay. This is within the X5, it's within the, register 5.
No.
One of those square things, okay.
Well, remember, we put this number, it's called an immediate, which is the address of the switches, we put that into register 5. So what this command is doing, this instruction is doing, it takes this, what's in front, adds it to this, which gives it the new address, that's the LEDs, and that's where it's gonna write the data that's in register 10.
Yeah, I was confused, because I mean, you're adding 3 16-bit values, and so I'm just wondering, is it matching that amount of bits, like on the output?
Well, yeah, if you're using any sort of half word command, like a load or a store, it's gonna take the 16 bits. So again, that's something that comes into test cases, right? Because you could run into like an overflow. I think that's what you're referring to.
Yeah.
Yeah, there could be a possibility of some sort of overflow, right? So that's, so that's where test cases.
What's the point of an address?
Oh, very great question. The address is what identifies, this data from this data, from this data, from this data, because the hardware, it's all the same. Registers are just registers. So I need some way to uniquely identify each piece of data, and I do that with an address.
So specifically in this example, it's just a way to like, you're giving this address to read from, basically.
Right, because see, it gets back to what this memory math IO means. See, what this means is that all input output devices have an address. That's how the microprocessor identifies it. It knows it by an address. Like the switches are at this address, the LEDs are at this address. Now, who determined this? The people that designed it.
Oh, okay.
Like Dr. Hummel, Dr. Cleanus, that they decided this. Now, it's one of those things where, like right now, you got to kind of take some things for granted. But by the end of the quarter, you'll know where this was decided. Like it's decided in one of those blocks. And who decided? Dr. Cleanus, Dr. Hummel.
Okay, so it's just like labeling locations basically. That's cool. Okay, so it's not actually that number that you're adding, the 11000. It's just gonna read a number from, or it's gonna read an unsigned value from that data location.
Right. Yeah, there's data at this address.
So is that the address or is that a 32 point? That 00 point, the output layer. And it's 0 by, is that 8 bits, or is that?
You tell me, this is telling you it's what? 0x tells you what follows. See, 0x tells us this is hex.
Okay.
And how many bits is each hex character? When we go 0 through well, we remember hex characters are 0 through F. So how many bits would you need for F?
4.
4. So each one of these characters is 4 bits. So this is 32 bits. Yeah, remember, see? Modern memory has 32-bit address. Okay, so the next thing I have to do is I have to get your groups, right? Because this is a 2-person group assignment. So let me do that now before you leave. When we get to the assignment part, you don't have to stay in the room if you don't want to. If you want to go somewhere else to work on it, that's fine. But don't leave yet until I get the group number.
Put some real things. There's some real plans.
Do you two want to be a group? Yeah, we work on the community.
Okay, so then. Yeah, mentioned the hardware stuff is another approach for.
Yeah, when they got further, toward the end. I don't know the project.
Okay.
Here,
After 11.
well, there's no class of 11. Yeah, so if you want to say, yeah, there's no class of 11 and 12 in this room, so if you want to stay, you can.
Okay, thank you.
Okay, so I got everybody in the group. Yeah, but you look at it.
I think so, yeah. Under all of this, our resources.
If I could have everyone's attention real quick, Derek here, is the ISA for this section, speaker notes 133, please graciously, offer his services here to, help out. Derek. Yeah, but the key point is like, see it, like somewhere along this line, right? You could come up with a result with more than the 16 bits.
So I'd say. So it's like the five. We're gonna use this.
Yeah, I mean, there's not that terminology. So it's just that, you know, we decided, you know, this problem, this needs 16 bits.
Yeah.
That's why we're using the half word. Like if you were gonna do like 8-bit unsigned value, then there's a load command, like if you look at the information set, there's an LV for load or byte. You know, no matter like how many bits you're actually having, there's a possibility, right? Depending on what values you're adding, that when you're done adding, there's a possibility you could have it over.
Like get around that. Start off. And then, make the result 32, so we don't have.
Yeah, it's great. Yeah, that's now, here you don't have that option, but yeah, if you were doing this with rear very observant.
don't really know.
Question?
Yeah. So a couple.
Okay.
Where
Well, it's not even just going. Like it doesn't have a column here. The way the way that look there, how it's treating the power. It's like in a description of the state somewhere. Right there. The online, it's called the assembler manual, and you see for each instruction it has detailed description. So like you asked about the what, LH? Yeah, it's in alphabetical order. So this is the LHU. So LHU, load, blah, 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 have word. Yeah, and then see right here, the half word read from memory is sign extended. So if you see sign extended, that means it's treating it as a sound. If you see the padding with 0, that means treating it unsigned.
So if we're gonna be using it like this, then should we replace this? We only like one. I guess you want to. You're saying this 0 year, but it's an X5. So if X5 is
Okay, well, remember, what we're doing here, we're not putting the value at this address. Okay, so let's define. We're just putting this address. Yeah, so it's adding this to the address, and then it's using that address. Here's the address. Find the content data from again, it's treating it unsigned, but that was there, treated signed.
Yeah.
That goes back to 133. What it was something I talked about at the beginning of the class. Well, now this is look through you,
Oh,
look to see what instructions you can.
okay, so this thing is just having a bunch of little tricks.
Well, this is the instruction set that goes with the audit, right? So, like we talked about in the class, that each microprocessor has its unique instruction set. Some have more instructions than others. Like you'll notice when you go through here, like there's certain ones you might think would be included. They're not. Like this doesn't have a multiply, it doesn't have a divide. Some do. Right, but you can multiply by successive addition, right? And you divide by successive subtraction. It's just that the more instructions you have, the more complicated it gets. So that's how these are each one.
Wait, what is this?
This is the this is the hardware. This is the hardware that runs up these instructions.
Does it define what these instructions are?
Yeah, you're gonna see that as we go through the course, that in order to come up with this, you have to know this. In order to understand this, like they're intertwined. Like you can't look at them separately. I mean, at the start here, we're kind of doing that, right? Because we're just getting started, but you'll see as we go through the course, you're gonna see constantly and saying, oh, well, the reason why this is like this is because that's how our instructions are. Well, the reason the instructions like this is because this is how the hardware is.
Okay.
Mhm.
Right.
Watch the video. Easier to watch the video.
There's no.
Yeah. Well, truck one.
I haven't seen it yet.
Which would not be. Well, I think that's that's not.
Yeah. So neither of them will.
So you don't have to.
No, I didn't. I tried downloading that. Like every time I open it, it just reinstalled.
Oh, okay, well, I have one other person.
Too bad.
Remember what the problems. What exactly are you adding?
I was trying to make it.
So how are you trying to change this? Yeah, you're doing this. Yeah. So if I have a two function, how would I choose? Not signing, it was at the very beginning of what you're talking about. Still working. There are two complements now, two complements of verb. See up on the board there, see 0010. What's that? Or what's that in basis? If we take that as a signed binary number, 0010. But it's a signed number that most of us give it. So it's the most, if you give it to 0, it's a 1. Okay. So that's a positive 2. So you see below. Yeah. Okay. What did we do below?
So you would flip them and add one.
Right. So if you flip in that 1, now what do we have? The 1110. What would that be? Negative. How do you get the magnitude?
That'd be 1101. Okay, so then
Can I ask you a question here tonight? I guess for this, what is the advantage, sort of, how do you know to use whether letting half word is a whole word?
Well, if you look at the instructions, we have load half word. So. I mean, it does which one you use depends on how many So here, the reason why is because both problem statements are told 6.
Okay.
But in this one we did in class. That's why.
Okay.
But here, for the one you're doing, you're treating the data as two components. So if you look at L8, the one that right here, see if you look at the description, it's telling you that whatever's red is going to be sign extended. Well, when you see sign extended right there,
Okay. So because we're loading 16-bit numbers and 32 in a system where there's 32 at work. That's what we're doing now.
Correct.
Right.
Yep. So do you flip the most significant bit or?
Yeah, you flip all of these. See, because if you look at what's up on the board, right, see how all the bits are flipped, right?
Yeah.
And then you add one.
Yeah.
So now, 1110, what is that? Well, oh, I see what you see, yeah. What you're doing is, you're making the most significant time. That's correct. But to get the magnitude, you don't count on this number, you just don't. think the bits are good. Because in two's complement. It's been complement, 9,007, not negative 0. You want getting back to that, see, if you don't have any binary number, you put this positive like that, right? Positive 2. We did this, yeah. Yeah, because see, the point is, see, there's reduced complement and now, right? You know, you have a list that shows like all the possible values. Yeah, that would be, but then there is complement. And you hate the two scores, eight value to start with. So you see, we started with the positive 2. We flipped the bits, we add. That's negative 2. Flip the bits, 0, 0, 1, and add 1. This is what's complement numbers.
Since you're not giving your results in the morning, we have to do it tomorrow.
That's what,
It's just like,
that's what you gotta figure.
Things is needed.
Yeah, let me, I'll answer, I'll give the answer to the whole comments. If I could have everyone's attention for a moment, Darcy here asked a question I want everyone to hear the answer to. And basically the question is, well, how many test cases should there be? Remember, you're getting evaluated. That's part of the evaluation is coming up with the test cases. And there's no like one answer to that because it depends. But what I can say is that you want enough test cases that show the full functionality of whatever you're testing. And also you want to make sure that you test like fringe cases, right? Like in other words, you're trying to break it, you know, like a question that came up during the lecture or towards the end of the lecture was, you know, well, is it possible that your answer could be more bits than, you know, the numbers you're adding, right? Which would be an overflow, right? So I mean, that would be something, because that's like a fringe case, right? So that would be something that you would want to check, you know, like 0 is typically a fringe case too, sometimes. Now, not to this assignment, but in hardware assignments, you might have a case where you got 2 inputs, like a reset and a load, let's say. And, you know, when one is enabled, that should happen. When the other is enabled, that should happen. But what if both are enabled, right? That kind of stuff. So, yeah, I'm not gonna give you what the test cases are. I'm not gonna tell you how many there should be because that's part of what I want you to think about. I would say that's probably the toughest part of what you have to turn in is coming up with test cases. And I expect that a lot of people are not gonna have like all the test cases, but going through the process, eventually you'll learn and I'm sure you'll get better as the course goes on.
In the video, I didn't see anything about where to run the test bench on the RISC-V.
Yeah, there is no test bench.
Okay, so then how exactly are we supposed to run? Or test, or use a test case.
Okay, well, I do show, in the video, like how you put the data in for the switches.
So does our test case submission look like a screen recording then, of us just like going through
That's-
each step?
Look at the criteria on Canvas, because I think it tells you to put it like in a table. Yeah, yeah. This is the running